Right. So last Tuesday, we have shown that a complex function given by a Lorentz series is analytic in its convergent open annulus. All right. So I will state in the following theorem that a Lorentz series has uniform convergence property in a subset of the convergence open annulus. Okay. So we let okay, so this is Lorentz series. About the point z equal to z sub 0 with convergent open annulus A of z0 beta and 1 over alpha. Okay, then the Lorentz series converges uniformly in the closed annulus A bar center at z sub 0 R1 R2 whenever beta is less than R1, less than or equal to R2, and less than 1 over alpha. Okay, so the situation is here. So this is z sub 0. Right, so this is beta, and this is 1 over alpha. Okay. So we have convergent open annulus. Okay. So this is the convergent open annulus. Okay. So if we select R1, which is greater than beta, so this here, okay, so this is R1, and R2, okay, so R2 is greater than or equal to R1, but less than 1 over alpha. Okay, and so in the closed annulus here, okay, that is the closed annulus. So the closed annulus including the two boundary circles here. So in the yellow region, the Lorentz series converges uniformly. Okay, okay. So that is the and for proof, please see the lecture notes. Okay. All right. We recall that in chapter 15, section number 4, we have shown that for any analytic function, if we can find an open disk which is contained in the defining open set of the complex function, then we will have a power series representation. Okay. All right. So which means that any analytic function has power series expansion, and we know how to compute the coefficient of the power series, which is related to the nth derivative of the complex function at the center of the open disk. And we will show that that any analytic function has Lorentz representation. Okay, so first of all, we will give a concept called that functions representable by Lorentz series. Right, so a complex function f of z defined in an open set omega in the complex plane is called representable by Lorentz series in omega if to every open annulus A with center z sub 0, the radius of inner circle is R1 and the radius of the outer circle is R2, such that z is R1 less than R2. Right? So to every open annulus contained in the defining open set, okay, there correspond a Lorentz series summation and from minus infinity to infinity Cn z minus z 0 nth power about z equal to z sub 0, which converges absolutely to f of z, okay, in the open annulus. Okay, so which means that if a complex function, suppose that okay, suppose that this is omega. So a complex function f of z defining on an open set omega. So this is the our open set. Okay. It's called representable by the range series. If we find an open annulus, so for example, suppose we find an open annulus here. Okay, and the center. Okay, the center is outside of the. For example, in here, the center is outside of the open set omega. Right. So now this yellow open annulus, as you can see, is contained in omega. Okay. So this is the open annulus. Okay, open annulus. The center in this case obvious Z0 is not in omega. Okay, but the open annulus it is contained in omega here. Okay, and then because it is called, the f of z is called representable by the range series, is that for such an open annulus, we can find the range series. Okay, we can find the range series, and this range series will converge to the original function f of z, right? In this open annulus. Okay. Okay, all right. Of course, you can select an open annulus such that the center here, for example, the center Z0 is in omega. Okay. Right. So this is another open annulus. Okay, which is contained in omega. And for this open annulus, again, you can find a range series such that the range series will converge to the complex function f of z in this green open annulus. And of course that the two range series corresponding to these two different open annulus may be different. Okay. Right. And then we will proceed to show if f of z is analytic, then it is representable by the range series. Okay. Okay. So our job now, we will let f of z be an analytic function okay, in an open set omega in the complex plane. Now, so we assume that this open annulus is an open annulus contained in omega. All right, and so we let epsilon be a positive number. Okay, such that R1 plus epsilon is less than R2 minus epsilon. Okay. All right. So again, we will consider open set, and we suppose that we have an open annulus so this is Z sub 0. So in this case, Z sub 0, the center is outside of the open set omega. Okay. And this is R1. This one is R2. I suppose we can, because R1 is less than R2, okay, so there must exist an epsilon, a pi number, such that we okay, so this is R1 plus epsilon, and this one is R2 minus epsilon, and R2 minus epsilon still greater than R1 plus epsilon, so that we have an inner open annulus. Okay. All right, so you can see the green open annulus is contained in the yellow open annulus. Okay, so we just let omega be in here. Okay. Okay. Now, so we see that we have that the closed annulus R1 plus epsilon, R2 minus epsilon, of course, is contained in the open annulus. Okay, so even if we conclude the boundary of the green open annulus, then it's still contained in the yellow open annulus. Okay. Now, because the f of z is analytic in omega, so of course z is analytic in the yellow open annulus. Now fz is analytic, okay, in the open annulus, the yellow open annulus here. All right, and we let gamma 1 and gamma 2 be the two boundary circles. All right. of the closed annulus A bar is 0, R plus epsilon, R1 plus epsilon, R2 minus epsilon. So that so that if the outer boundary okay, so this one is gamma 2 star, okay, and the inner boundary okay, so this one is gamma 1 star, okay. Okay, so gamma 1 and gamma 2, maybe I will say gamma 1, gamma 2, all right. Alright, so with the two boundary circles of the closed green annulus, the green closed annulus. Okay, with center E sub 0 and radii. Okay, the radii R1 plus epsilon and R2 minus epsilon. So gamma 2 is the outer circle, epsilon, respectively. Okay, and both oriented counter clockwise. Okay, so the orientation would be this way. Okay, so it's counterclockwise oriented. All right. So now we focus on the yellow open annulus here, and we see that and the two closed paths, gamma 1 and gamma 2, are inside the yellow open annulus. Okay, so it is clear that the index of the cycle gamma 2 plus minus gamma 1, okay, of the z is equal to 0 for all z not in the yellow open annulus. Okay. Why? Well, if this is outside the yellow open annulus, for example, they are if in here, if we have z here, then we know okay, so we know that for let's see the reason. Okay, all right, so for z with z minus z0 has distance greater than or equal to R2. Okay, so in this case z is in here. Okay, so the distance between z and the center z0, okay, will be greater than or equal to R2. Okay. Now, for this case, then the index of gamma 2, z is equal to 0, and the index of gamma 1, z is also equal to 0. Okay? Right? Because it's here. The two circles do not enclose z at all, right? So their index will be 0. And so which implies that the index of the cycle gamma 2 plus dot plus minus gamma 1, which is index of gamma 2. Oh, sorry. Z minus index of gamma 1 z, which is 0 minus 0, which is 0. Okay, for the case. Now for z with z minus z0 is less than or equal to R1. Alright, so this case corresponding to a point here, z here. Okay. So the distance between z0 and z is less than or equal to R1. Okay, so z can be on the boundary on the circle with radius R1. Okay. All right. Now for this z, you can see that the index of gamma 2 is equal to 1, and the index of gamma 1 of z is equal to 1. So which implies that the index of the cycle, okay, so the cycle is just the gamma 2 dot plus minus gamma 1. So this index will be so this is 1 minus 1 is also equal to 0. Okay, so this shows that whenever z is not in this yellow open annulus, then the index of the z, all right, with respect to this cycle is equal to 0. Okay, it's equal to 0. And then furthermore that okay, since gamma, which is defined to be the cycle is right, has gamma star. The gamma star is gamma 2 star union gamma 1 star contained in the open annulus. Okay, so by global Cauchy's theorem, so by global Cauchy theorem, we have that f of z times the index of the gamma. Okay, so the gamma is equal to gamma to dot plus minus gamma 1 of z. Okay, is equal to 1 over 2 pi I, and gamma 2 dot plus minus gamma 1, and f w minus z of dw. Okay, so this is from the global Cauchy theorem. Okay, because we have these premises here. Okay, this is required. All right, this is quite required here. Okay. So we now have this one. Okay, and by definition, this is equal to gamma 2 fw w minus dz dw minus y 2 pi I gamma 1 fw w minus z dw. Okay, so this become two line integrals. Okay, and okay, so now what is the index of z? And this is true for all z. Okay, for all z. Okay, in the z0, R1, R2 exclude gamma star. Okay. Now we are focused on the points, the z, inside the green open annulus. All right. So now for z in the green open annulus, okay, because the green open annulus is in here, all right, it's in here, all right. So we know this is contained in the yellow open annulus minus gamma star. Okay, so we know that. So now for A in that, we know the index of gamma 2. Okay, so that for point inside, so in here, z is here. When z is here for gamma, for the gamma 2, for the outer circle, the index is equal to 1. Okay, and the index of such a z, right? Okay, with respect to gamma 1 is still 0. Okay, because the inner circle does not enclose z here, so that the index is 0. And so, which implies that the index of gamma, which is bigger gamma, which is gamma 2 plus minus gamma 1 z, this is equal to index of gamma 2 of z minus index of gamma 1 z. So it's 1 minus 0, which is equal to 1. Okay, so we know when z is in this green open annulus, okay, then thus, so now we know that f of c, okay, so the complex function itself becomes to the difference of two line integral. One is over gamma 2, all right, the other is over gamma 1. for all Z is in the green open annulus. Okay, so for all Z in this green open annulus here. Now the first, all right, so the first line integral becomes to non-negative power series or just power series. Okay, so 1 over 2 pi I gamma 2 f of w to minus z and the dw here is equal to and equal to 0 to infinity Cn z minus z0 n's power. Okay. Right, where we know the Cn can be computed, which is 2 pi I of the gamma 2 of Fw and W minus Z 0 to the n plus 1's power of dW. Okay, right, as shown in the proof of theorem 15.4.8. So in this theorem, we have shown that every analytic function is representable by power series. Okay, so in that case, we have shown that the analytic function is equal to, right, that a line integral here. Okay. All right. So the procedure will be the same. So I will not repeat here. All right. So the first line integral here, right, becomes to be a power series. Okay. Okay, and right. So, and with a similar argument, right? So again, please see the lecture notes. Okay. As in the proof of theorem 15.4.8, we have here minus 2 pi I gamma 1 Fw the minus Z and the dW. Okay, so that is the second line integral. Okay, becomes, all right, so the second line integral here, so this is the second line integral, is minus of this. Okay, and so we know this is 1 over 2 pi I gamma 1 Fw now Z minus W and the dW here. And as in the proof of theorem 15.4.8, that this function, all right, this function of w, when z is fixed, and the function of dw is actually is the limit or the sum of this okay, right? So so as in the we have that we have that this is series sum converge to, so this is series sum actually, it actually converges uniformly. Okay, to, right, so this one converges uniformly to f of w divided by z minus w. Okay. For all w is in gamma 1 star. Okay. So if we consider this is w as in the gamma 1 star, okay, then this is a series of functions of w, okay, and which converges uniformly to this function. Okay, so this one converges uniform to this function, and again by the by a theorem, okay, if this one converges uniformly, we know that we can exchange the order of line integral and the summation. So this is becomes to be 1 over 2 pi I gamma 1 and the w minus 0n fw divided by z minus z 0 n plus 1 dw. Alright, and this is by theorem 15.5.3. Okay. Right? So if this series converges uniformly, okay, so this is important to have. Okay. All right. So so we have this result. Okay. And the procedure, the argument is very similar to the argument in the proof of theorem 15.4.8. Okay, so you can see the lecture note for the details. Okay, and so we have this one now. So now this becomes 2. And as you can see, this is 0, infinity, and 1 over 2 pi I, and the gamma 1, and this is w minus z0 to the nth power, and the f of w okay, f of w and the dw. Okay, so this one, and z minus z0 and minus n plus 1. Okay? Alright, so because this term is independent of w, so we can move it out. Okay. And we change the index so that the index will, so we will see that this is summation n from 1 to infinity and c minus n, z minus z0 minus n here. Okay. Okay. So this is, you can see this is become to a negative power series. You can see because the power are all negative powers. Okay. Now, where c minus n, so we can see as c minus n is equal to 1 over 2 pi I, and the line go over gamma 1, and here is w minus z0 minus 1, f of w, and the dw. Okay, and so we can write it in the following way. Gamma 1 f w and the w minus z0 to the minus n plus 1 and the dw. Okay, so this is minus n plus 1 here. Okay. So now we have shown that the first 90 here, okay, is equal to a non-negative power series. Okay. And the second line integral is equal to the negative power series. So that's we have that f of z is equal to summation n from minus infinity to infinity, and the cn z minus z0 to n's power for all z in the green open annulus 1 plus epsilon up to r2 minus epsilon. Okay, and where the coefficient will be 1 over 2 pi I gamma 2 and the f of w and the w minus z0 n plus 1 d omega if n is greater than or equal to 0, and the other will over gamma 1, and the integrand is again equal to the minus z0 and n plus 1 dw if n is then equal to minus 1. Okay, so you can see that we have the same n here, but you should know this n here is all non-negative, but this n are all negative integers. Okay, so basically you can see that you have the same format of the integrand, but over different closed paths, for non-negative n, you over the gamma 2. Okay? So gamma 2 would be this one, okay? The outer green circle, and the gamma 1 will be the inner green circle here. So you have that. Okay. Now, since f of z divided by z minus z0 to the n plus 1's power, okay, this one is analytical. All right, in the yellow open annulus, 1, 2, for all n in z. Okay? Because this open annulus is contained in omega. Okay? And f of z is analytical in the open cell omega. So of course, so fz is analytical already. And you can see that the denominator is also analytical functions. Okay, and it's never a 0, okay, for all z in this open annulus. Okay, right? Because in this this is an open annulus, so z0 is not contained in this open annulus. Okay, and so that, and then we will look at the index of gamma 1, z, and the index of gamma 2z, which is equal to the index of all gamma. I will describe for all z not in the open annulus. The yellow open annulus. The reason is that because gamma 1 and gamma 2, they are oriented counterclockwise. So if z is in here, right? If the distance of z from z0 is greater than or equal to r2, okay, then the index over gamma 1 and index over gamma 2 will be zeros. Okay, will be zeros. And for any gamma, and suppose gamma is here, gamma would be all right. So the gamma okay. So this is a closed. This is a simple so this is called gamma. All right. So gamma is a simple closed path. Okay. Enclosing the circle centered at z0 and radius, so with okay, so gamma is the a simple closed path enclosing the circle with center z sub 0 and radius R1. Okay, see here R1 is the inner yellow circle here. Okay, R1. Right, enclose that. All right, so a single closed path. Oh, by the way, and this is with gamma star contained in the open annulus. So I have to describe that. So it's a simple closed path with gamma star contained in the open annulus. All right, in the yellow open annulus. Okay, and which enclose the circle with the center d sub 0 and radius R1. 1. Okay, the center R1 here. All right, so they will be the same. Will be same. Why? If you want to explain, you can. Okay, so for this analytic function, and we know the index. This is for z with the distance greater than or equal to R2. Then we know the index gamma 1 z equal to the index gamma 2 z equal to the index of any gamma, which is equal to 0. Okay, and for z with z minus z0 less than or equal to R1, then the index of gamma 1 z is equal to the index of gamma 2 z equal to the index of gamma z, which is equal to 1. Okay, so you can see. So if z is here, then the index of the orange simple closed path, the green outer circle and the green inner circle. So for these three simple closed paths, the index of z will be 0. But when z has distance less than or equal to R1, right? Now you see that the index with respect to these three closed paths will be equal to 1. So that they are all equal. Okay? They are all equal. Right? And for all the points outside this open set, and we know this function is analytic, right, in the open set. So again, by the second statement of the global Cauchy's theorem, okay, now so the integral of the analytic function over gamma 1 will be equal to the integral of the same function over gamma 2. Okay, and also equal to over gamma. Okay, so this identity is by the global code theorem. Okay, so we look at, when we look at here, okay, so we know that this two line integral can be replaced by this integral. Okay. All right. So so that we have the Cn can be replaced by 2 pi I of gamma f of w minus z0 raised to n plus 1's power for all n integer n. Okay. All right, and so now we can state another main theorem here. Okay, and this is actually a restatement of theorem 16.1.1 in the textbook. It's called the Lorentz series representation of analytic function. Right, so the statement is easy. An analytic function f of z, okay, defined in an open set omega is representable by the Lorentz series in omega. And specifically, to each open annulus, okay, A sub 0 and R1, R2 in the open set omega, there corresponds a Lorentz series expansion of f of z about z equal to z0. Okay, so this expansion will be here. As power. Okay, with the Cn is equal to 1 over 2 pi I and gamma Fw W minus Z0 to the n plus 1's power, and the dW Z, where gamma is any simple closed path in the open annulus, which is the yellow open annulus, which encircles the inner circle with center Z sub 0 and radius R1, oriented counterclockwise. Okay, so we should orient that counterclockwise. Okay, so this is the statement is a little bit from the statement in the textbook, and so this one is I think this is the most general statement we can have about analytic function. Okay, defined in an open set, not necessarily a domain. Okay, not necessarily open connected. Just any open set omega would be true. Okay. Any questions? So I will take a couple of examples to illustrate the usage of this theorem, as well as theorem 15.4.8 in chapters 15. All right. So Fz is equal to 1 over 1 minus z, okay, which is analytic, okay, in the open set omega, and omega is just the whole complex plane, but without the point 1. Okay, so there's only one singularity here. So except this point, right? This is 1. Okay. So omega is C, right? So this function is analytical in this open set. Now, we look at the unit circle. So that, and now inside we have an open disk, right? So so the center is 0, is the origin, and the radius is 1. Okay. Now we know this open disk is contained in omega, in the differential set. Right? So things here. Now, by theorem 15.4.8, Fz, this Fz is representable, right? Or we say Fz has a power series representation or power series expansion, okay, about z equals 0. All right, and we can find them. Okay, so this is summation. All right, and we know factorial z and power. Okay, right. So this power series expansion is just a Taylor series expansion. And when we evaluate the nth derivative, we find that this is actually equal to 1, and so this is equal to, and here. All right, and this representation is good for all z in the open disk with the center 0 and radius 1. Okay, so this series representation only good for this. All right, this is only good for this. Okay, and note that, so this power series, if you know that, the ROC, okay, so it's ROC, right, its radius component is 1. Okay, if you do the retest, right, so because alpha is equal to 1, okay, alpha is equal to 1, so you can see that. Okay, but if we check, so this is inside, but how about the outside? The outside here, the outside actually is in open annulus with the center 0 and the 1 and infinity. Okay? So the outside of the cursed disk is the open annulus. Okay? Here. So now furthermore, the open annulus A 0, 1 up to infinity, okay, is contained, right, in omega, okay, which is C minus 1. Okay, and now, so by theorem 16.1.1, okay, f of z, which is 1 over 1 minus z, okay, has a Laurent series expansion about z equal to 0. All right, and this you can compute it. You can see that this is 1 over 0. So you can do it in the following way. It's z and 1 minus z minus, okay? And so that n equal to 1 to infinity minus z to the minus nth power for all z in the open annulus. Infinity. Okay. So you can see if z minus, okay, if z minus has magnitude less than 1, then it will converge. But z minus, the inverse of z has magnitude less than 1, which means that the magnitude of z will be greater than 1. Okay, so that z will be in here. Okay. All right, so you see here that this is the Lorentz series expansion. And the Lorentz series expansion, you can check back to see that what is the alpha and the beta. Okay, so let's see. This Lorentz series, okay, has alpha, so it's lim sup and goes to infinity. But as you can see, the positive power has 0 coefficient. So alpha is 0, which implies that 1 over alpha is infinity. Okay, that's why we have infinity here. And the beta, lim sup c minus n, and we know this is is 1, so this is equal to 1. Okay, so beta is equal to 1. So you can see this is actually the convergent open annulus of this Lorentz series. Okay, so this Lorentz series contains only negative power terms. Okay. So it's very interesting, at least in this example, the same analytic function here, right? This is the same analytic function. And this analytic function, if you find an open disk, okay, in the defining open set, like this one, like the disk here, which this open disk is contained in the defining open set, then we have a power series representation. Okay? But if we find an open annulus, all right, like this one, in the defined open state, then we will have a Lorentz series representations. Okay, okay. So as you can see, if Z is in the open disk here, you have Lorentz series expansion. But if Z is outside the unit circle, then you have a Lorentz series expansion. Okay, but on the unit circle, you don't know. Okay, so on the unit circle, you don't know that. Okay. Any questions about this example? And now another example. If we consider a rational function okay, this rational function is analytic in the open set omega, which is the compass plane minus 1 and 2. So that you can see here, This is 1 and 2. Okay. So except these 2 points, this rational function is analytical. Okay? For that. And by partial fraction, we know this is 1 minus 2 plus 2 minus z here. Okay, so it's the sum of 2 rational functions. Alright, and we have experience about the expansion of this kind of functions. Okay, so we expand. So we can expand 1 over 1 minus z in 2 different ways. As in the previous example. Okay, so 1 over 1 minus z can have the power zero expansion for all z in the open disk, center is 0, and the radius is 1. Or you have the Lorentz series expansion minus z minus n for all z in the open annulus with center 0, right? And with inner radius 1, outer radius infinity. Okay, so we have this one. And similarly, right, so we can expand 1 over 2 minus z in 2 different ways. As follows: 1 over 2 minus z is equal to 1 over 2, 1 minus z divided by 2. Okay, so this is summation n equal to 0 to infinity, 1 over 2 to the n plus 1's power times zn. Okay, for all z in the open disk with radius 2. Okay, with radius 2. And also, this is equal to minus 1 and z, 1 minus 2 divided by z, so that this is equal to 1 to infinity, minus 2 to the n minus 1's power, and z minus n for all z in the open annulus here. Now, so from here, we know consider the so this is the open disk with center 0 and the radius 1. Okay. And we have an open annulus with inner radius 1 and the outer radius 2. So this is center 1 and 2. And the last is an open annulus with inner radius 2, but outer radius infinity. Okay. Okay. All right. So you have that situation. So you have this inner, and you have the green annulus, and then you have the red open annulus. Okay. Now, so first case, the disk is contained in the omega. Okay, put the case here. So now, by theorem 15.4.8, now Fz, which is minus 2z plus 3, z3 minus 3z plus 2. Now has representation so that in this open disk, then these two will be valid. Okay, so this is, it becomes to be summation n from 0 to infinity, and 1 plus 1 over 2 to the n plus 1's power, and Zn. Okay, so you can see this sum. Okay, so you have this power series expansion. Okay, for all z in the open disk with radius 1. Okay, now the second case, the open annulus with inner radius 1, outer radius 2, also contained in the defining open set. Okay. Now, which one cover this open annulus? Okay, this one, right? This cover the open annulus here, and this one, again, these two. Because the open disk has radius 2, so the open disk, this open disk contains this open annulus, right? Also, this open annulus contain this open annulus too. So that, in this case, the f of z has, now we have, so this one and the other. So we have summation n equal to 0 to infinity, 1 over 2 n plus 1 Zn plus summation n from 1 to infinity minus z minus n minus. Okay? So we have here so this is a Lorentz series expansion. Okay. Because this consists of the positive power, this is the negative power. Okay, for all z in the open annulus 1 and 2. And then the third condition, the third case is that the open annulus is contained in omega. All right, so, okay, this is by theorem 16.1.1. Now, by theorem, again, by theorem, 16.1.1, then f of z minus 2z plus 3, z squared minus 3z plus 2. Now, for the third case, we know this open annulus, right, is contained in this open annulus and also in this open annulus. So the expansion will be the sum of these two terms. So this is n from 1 to infinity. And we have minus 1 plus 2 to the n minus 1's power, z to the minus n. Okay? So you have this Lorentz series expansion here. And this Lorentz series expansion contains only negative power. Only negative power here. Any questions? Okay. All right, so the representation of an analytic function, either by a power series or by a Lorentz series, depends on finding an open disk. All right. Inside the defining open set, or finding an open annulus. Okay, when an open annulus contained, all right, in the defining open set omega. Okay, if we find an open disk contained in the defined open set omega, then you can have the power series expansion at the center of the open disk. Okay. On the other hand, if we can find an open annulus contained in the defined open set of an analytic function, then you will have a Lorentz series expansions at the center of the open annulus. Okay, so it depends. Okay, and you know how to find. Of course, if you want to find them, then you have the coefficient. We have given you the way how to find the coefficient, right? But in some situation, for these simple cases, that you can find the expansion immediately. Okay, you can find some algebraic manipulation. Okay. Otherwise, you have to deal with the line integrals. Okay, you have to do line integral, which is a little bit more time-consuming. But in principle, you can, of course, you can find the coefficient by evaluating the line integrals associated with. All right. Okay. So that so you have that. Okay, and so the next section we'll talk about the singularity. And the zeros of analytic functions. All right. First of all, about singularities. So a complex function f of z is said to have, to said to be singular, or said to have a singularity at a point z equal to z sub 0 if f of z is not analytic, or perhaps not even defined at z equal to z0, but every neighborhood so every neighborhood is actually a disk with radius epsilon centered at z0 of z sub 0 contains points at which fz is analytic. Right? So fz has a singularity at the point under two conditions. One, fz is not analytic or even not defined at that point, z0. Second, for every neighborhood of z0, we know a neighborhood of z0 is actually an open disk with a center z0 and with some positive radius. So in such a neighborhood that contains points at which fz is analytic. Okay. And in this case, z0 is called a singular point of the complex function. Okay, now a singular point z sub 0 of f of a complex function f of z is called isolated if f of z is analytic in a neighborhood, in a small open disk, except at z0. Okay. All right. So let's take an example. The tangent z. Okay. All right. Tangent z has isolated singularity at the point here, which is plus minus pi over 2, plus minus pi 3 pi over 2, plus minus 5 pi over 2, etc. Okay? So we know that. And tangent 1 over z has a non-isolated singularity at z equal to 0. Okay, of course it has singularity at z equal to 0 because 0 cannot be a denominator. But for any neighborhood of the 0, you can find a point such that this is analytical. Okay? Right. So this gives us 2 examples. Okay, we have. Right, so we consider isolated single point first. So let's see for tangent z. Okay. Right. So tangent z is analytical at all points of the complex plane except this point, this countable many points. Okay. So that's tangent z. Okay. Now if z0 is an isolated singular point, of a complex function okay, of an analytic function defined in an open set omega okay, so I think I found an error in my notes. Okay, so suppose V sub 0 is an isolated single point. Okay, so so maybe this is omega. Okay, and Z sub 0 is an isolated single point, so that we can find a neighborhood. Okay. And in this neighborhood, all the points in this neighborhood is analytical. So which means that, but except the center is 0. Okay. All right, and so here we have an open annulus. So now, so in this open annulus, so we have an open annulus with Z0, 0, and say R. And this kind of open annulus we will denote it as D prime, Z0R. So that is the open disk with the center Z0 and radius R, but we delete the center z0. Okay. So this is called the deep prong. So deep prong actually is an open annulus with inner radius is 0 and outer radius r. Okay. So that this is equal to z in C such that okay, so the distance is greater than 0, but this thing r. Okay. All right. So for such an isolated then by theorem 16.1.1, Fz has a Laurent series expansion at about z equal to t0. So it's f of z equal to infinity and Cn z minus z0 nth power. Okay, in a punctured open disk deep prong of z0 and r. Okay, so the punctured deep prong is the punctured open disk, means that we puncture the center out of the open disk. Okay, so that, and we know this is actually z0 and 0 and r. So it is clear that the beta, okay, lim sup all right, of the nth root of the absolute value of the coefficients corresponding to the negative power, this beta must be equal to 0. Okay, this is for sure. Okay, so if 0 is the isolated single point, I think we have this result. Okay, so around the single point, the analytic function has the Laurent series expansion. Okay, so this is for all z in the punctured. Okay, for some r. Okay, the r is selected. You make it as big as possible, but anyway, you have neighborhood there. Okay, so you have this. Now the negative power series summation n from 1 to infinity and c minus n and the z minus z0 to nth power. So we have this. Then this negative power series, this one, is called the principal part of f of z, okay, at the isolated singular point. Z equal to z0. Okay? So for one isolated point, now there is associated with negative power series. Okay. All right, if the principal part has only finitely many terms, i.e., it's the principal part 6. Okay, with C minus M not equal to 0 and C minus N equal to 0 for all N greater than equal to M. Okay, if we have that, so if the principal part is here, then Z0 is called a pole of order M. So a pole of an analytic function, okay? So a singular point of an, an isolated single point of an analytic function is called a pole of order M if its principal part has only finitely many terms, okay, and the smallest negative power with non-zero coefficient, all right, give us the order, okay. So if up to C minus M, all right, C minus M, with M is the smallest one, which is non-zero, then this M is called the order of the pole, okay. And a pole of the first order is called a simple pole. All right, and if the principal part has infinitely many terms, okay, then Fz is said to have at z equals z0 an isolated essential singularity. Okay, so now we classify isolated singularity point into two classes. One is called poles, the other is called essential singularities. Okay, and it depends on the principal part of the isolated single point. Okay, so if the principal part has finite many terms in the, then we call it a pole, and we know how to find its order. Otherwise, it's called an isolated essential singularities. Okay, so you have to have the okay. So isolated, because these two classes of isolated singularity have different behavior. Okay, in the complex analysis here. Okay, so so we have to treat them in different way. Okay, in different way. So, okay. So, any questions? Okay. Okay. So, if no questions, I stop here.